Good morning, everyone.
Good morning.
You guys doing good?
Yes.
Excellent. Let's go ahead and resume with multiple regression. This will be your next homework. I know a lot of this we've already had in 6022, but again, with statistics, it's not bad to have some redundancy. And so you'll be getting practice on doing things you've already done in 6022, but will apply to many of the multivariate techniques. Again, multiple regression is when you have how many predictors?
Two or more.
Two or more. And how many outcomes?
One.
One. Even though at the end of the chapter, you're going to actually learn a new technique called multivariate regression. When you actually have multiple predictors and multiple outcomes. And we'll get to that at the end. And that'll be multivariate regression. But for now, we just have this, right? We just have 3 x's predicting 1 outcome. So we already discussed multiple regression. We went thoroughly through simple linear regression. And now, let's talk about collinearity. Someone tell me again what collinearity means, or multicollinearity, as you remember from 6022. What does collinearity or multicollinearity mean? Between predictors. And what's the chances, Ross, that you're probably going to have, at least in applied research, what's the chance you're probably going to have collinearity between predictors? Pretty high, isn't it? So, has anyone started thinking about a topic for their dissertation? Has anyone started having an idea, something you're interested in?
Yeah.
Like what?
Assessments for to determine the readiness in end-of-life situations.
Okay. What's your outcome?
The outcome would be a variety of outcomes. Really.
Give me one.
So,
in medicine, sometimes in clinical trials, they have what's called a primary efficacy endpoint, which is your main outcome. Then there may be secondary ones. What would be your most important outcome?
satisfaction.
Satisfaction with?
The hospice service.
Okay, so let's do satisfaction with hospice. What might be a good predictor of satisfaction with hospice?
If you would choose that group again.
Okay, likelihood of using again, right? That's a big predictor in, sometimes it's actually an outcome in customer satisfaction. Likelihood of choosing. What would be a second predictor?
If you would rate the service that you received as providing everything that you needed.
Okay, rate service, and give me a third. Satisfaction, likelihood you would choose it again.
So rating of the service, and then rating of, like the logistics. Was the paperwork taken care of?
Sure, absolutely. Do you think those 3 will be related?
Yes.
Do you think rating logistics, rating service, and likelihood you would choose again?
Yes.
Absolutely. So this little part there, as Ross said, the likelihood of R12, R13, R23. The likelihood of there being relationships between the predictors is pretty high. Right? So here, collinearity focuses completely on what, everybody? The x's or the y? The predictors or the criteria?
The y.
Yes, exactly. So collinearity only focuses on the predictors, right? And we have 3 predictor model. Such as Stacy's. Stacy's study. Is that how you do plural Y apostrophe S? If I do that, it's Stacy's study of hospice satisfaction, which is Y, right? So X1 might be satisfaction with the rating of logistics. Right, like such as paperwork. X2 might be likelihood. Choosing the hospice again, right?
Right.
Which I want to make this note, which could also be an outcome. Just so you know, Stacy, that could also be conceptualized as an outcome.
Sure.
A lot of times you'll see that in customer satisfaction as an outcome. So it could be a predictor or an outcome, depending how you define it. And X3 would be rating of service. And we probably have intercorrelations, don't we? And that's the term we use, right? Remember everybody from 6022, intercorrelation, which would be R12, R13, and would be the last one, everybody? R2. So you probably got some intercorrelation, don't you? All three of those. So one thing you got to do, and you'll do this as part of your homework, is to diagnose the extent of collinearity. In other words, just look at the intercorrelation matrix. Look at the intercorrelation matrix, everybody. So how do you diagnose it? So first of all, first way to diagnose, DX means diagnose. Collinearity is scan the correlation matrix. Only focusing on what, everybody? Only focusing on what? Focusing on the predictors. Or sometimes what you're going to see some software call it, everybody, covariance. Even though I know covariant has a special meaning in ANCOVA, sometimes you'll see often that the list of x's are called covariance, especially when they're continuous level. So you want to kind of see that some software will call it covariance. A diagnostic that you can see in SPSS is called tolerance, which we went over in 6022. But let's go ahead and let's look at tolerance right here. So here you see, I know it's hard to see, but you get this called tolerance, of which each IV is serving as a DV. Each IV is serving as a DV. So here we have three predictors: exercise, health maintenance, and social influence, predicting the outcome. And as you recall, that serves as a DV. And you recall, we would love tolerance to be close to 1.0. We would love it to be close to 1.0. Because think if there's no intercorrelation, where I and J are two predictors. Think if there's no intercorrelation. What's 1 minus 0? 1 minus 0 would be what? You got it. Maximum value is 1 minus 0, right? If no intercorrelation. That would be the best case. So you would love to have R120, but in applied research, that is not a probable outcome, is it, everybody? As Ross was saying, you probably got collinearity. Probably going to have collinearity. And sometimes, again, you can just look at correlation matrix. Let me see if, yep, I kind of pasted it right here. Scan the correlation matrix. And there you go. There's the 0.405, 0.393, 0.4. Not horrible, but moderate. Thing is, they're about as high as some of the predictor criterion relationships, so it's almost a push, it seems. So this is where you'll be focusing on. So each of these serves as a DV for the other predictors, which means social influence becomes a DV for exercise and health maintenance. Health maintenance becomes a DV for exercise and social influence. So the tolerances here, everybody, are 0.67, 0.77, 0.77, 0.7. They're almost all the same, because they have very similar pattern of correlations. So that probably means there's about 22% of variances accounted for predictors for health maintenance. 22 there, about 23 there. And that's tolerance, everybody, which is a good diagnostic. We'd love to be close to 1.0, but that ain't going to happen. So that's one way to diagnose your model. And how to get this in SPSS? You just go to Analyze, Regression, Then you went to linear. And then you put your dB here. And then all your predictors. And then your statistics, you'll hit this thing called linearity diagnostics. Exactly what you did in 6022. Linearity diagnostics. And that'll get you everything you need. So, some textbooks will say, don't worry about tolerance unless it's less than or equal to 0.1. However, I disagree with that, and I'll tell you why. That means your intercorrelations are greater than 0.9. Because think what it takes to have a tolerance of 0.1. Right? Tolerance would have to equal 1 minus 0.1, right? 0.9, which equals 0.1. Right? Does everybody see that? Remember, that's an R squared. So R squared equals 0.9. That means 90% of variance is accounted for with the other predictors. That's huge. My own red flag, this is again just my own opinion, everybody. My own red flag is if I see intercorrelations about 0.5-ish. There's no hard and fast rule. Some would say that's way too conservative. Some don't even worry about linearity. But I start seeing some problems with 0.5-ish. So hence tolerance of 0.75-ish is when I start getting a little bit of my own internal red flag. So you may want to use that as a guiding point. A guiding point. So that's tolerance, everybody. The inverse of tolerance is called the variance inflation factor, the VIF. And variance inflation factor is just the inverse. It's just the inverse. Which means 1 over tolerance. Right? When I do tol minus 1, right, you see the minus 1, that means 1 over tolerance. So, 0.767, what's 1 divided by 0.767? Is 1.3. Is 1.3. And look here in SPSS, everybody. 0.767, there's VIF, 1.3, right there. There's the variance inflation factor. You don't have to report both those, everybody, because one is really a function of the other. Usually I tend to focus on tolerances. The VIF, if we like the tolerances to be higher, given that variance inflation factor is the inverse of tolerance, do you want that to be higher or lower? Given we want the tolerance to be higher, given that VIF is a function of being the inverse of tolerance, we probably want it lower. You got it. You got it. So, what's the inverse of 0.9, everybody? So if we took the liberal stance of 0.10 of tolerance to be problematic, which is what the book says. The book says 10.0, 1 divided by 0.1 equals 10. Right? Remember they said a tolerance of 0.1 is problematic? Some say a VIF greater than 10 is indication of linearity, of severe linearity. Well, I think that is way too forgiving, in my opinion. So that means you got correlations of 0.9, which means you've got like SAT math, SAT math, SAT the writing, and the SAT reading, and the SAT total in the same model. Do you think they're going to be correlated? Because what? SAT goes up to 2,400, right? In fact, yesterday I was talking to a gentleman. His daughter is applying for Columbia. They're accepting like 1,000 out of 28,000 applicants, and tons of people, tons of 2,400s on the SAT. I mean, lots of people. Because you think, you got that 2,400, you're in, right? You're from San Diego school. You're competing with everyone else. He said, tons. There's quite a few, 2,400s. Isn't that amazing? And not getting in. Not necessarily getting in. So that being said, everybody, there are also, so you're going to look at the tolerance or variance inflation factor, whichever one you want for your homework. And even the book says, though no rule of thumb on values, it's generally believed that anyone exceeds 10 is there some concern, which is obvious. So, There's also this thing here called linear diagnostics, which you don't have to look at for your homework, but it gives you what's called these condition indices. Do you see these eigenvalues? Do you see that eigenvalue 3.916? It provides indications of how many distinct dimensions there are among the IVs. They say you don't want it to be higher than 30. So do you see that 21.69? If I took the ratio of the highest to the lowest, 3.9 divided by 0.08 to the square root, there it is. Which means potentially some linearity, but nothing really bad. I usually don't use this one, and I don't see many researchers use this to diagnose linearity. It's not easy to interpret. That is one other diagnostic you do get in SPSS. So, what are some recommendations the book makes? There's 3 ways of combating linearity. One is to combine predictors. Right? So, what can one do? Before you combine predictors, I'd be very, very, very cautious before I did that. Why? How many of you are taking a research methods class or have? How many of you learned about construct validity? Operationally defining constructs, thinking about what a construct means. So all of a sudden, if you have a 0.8 correlation, say you have a 0.8 correlation, or no, let's do like 0.68. Let's do something that says there's some overlap. You have a 0.68 correlation, and maybe one variable is job satisfaction, the other variable is job involvement. And they both have a core of 0.68. So I'm just going to combine them. What are you going to call them, guys? Go ahead, just give me a name. You got job sat, job involvement.
Engagement.
Okay, let's call it engagement. Okay, let's call it engagement. However, could you make an argument that though they're related, they're also separate? And I know that may sound a little bit contradictory, but you're going to learn about a thing called factor analysis, whether it be exploratory or confirmatory. And maybe the fact is, they're related and yet distinct. So you're going to be combining them, and that may or may not make any sense. So just because of a correlation, don't just willy-nilly start combining it without doing your due diligence in terms of the psychometric investigation. And these are really 2 distinct entities, or not. Because if you combine them, you're going to pretend it's this thing called engagement. That may not be correct.
You say is 0.7 kind of the tipping point?
There's no tipping
There's
point.
no tipping
No, people do come up with rules, 0.5, 0.7s, 0.8s. And I understand that. We want guidelines. But yeah, I mean, once it gets much more than 0.6, 0.7, you know, once you're beyond 0.7, you're talking at least 50% squared, right, shared variance, right? So that's quite a bit. But I always still fundamentally look at the entity and what I'm trying to measure. Right? Does it make sense to pretend they're all in one? Right? It becomes a global score called engagement. But before I would do that, I would do some type of factor analysis.
Is that when you would partial out the one to isolate the other?
Well, that you could just do in multiple regression when you look at semi-partials and partials. But here, factor analysis would tell me if I have 6 items I measure job sat, 6, that do they load on one construct? Is it a general construct called engagement, or do they stay separate? And we'll get into that with factor analysis. So be really cautious about ever combining predictors. A second way, if one has a large set of predictors, is to do what I just said in factor analysis. Exactly what I just said. I said principal components, combine predictors, EFA, and I am just called exploratory factor analysis. EFA or CFA. I want to add that confirmatory, which is going to be your final project you're going to do in this class when you learn structured equation modeling. The third way is to use a technique called ridge regression. Remember we went over ridge regression last week, and I showed you that you can actually download a macro from SPSS right there. I showed you the macro. I've only used ridge regression on one project in the whole year. So what it does is it adds a little bit of a constant to the variance. But I haven't used ridge regression very much, and I honestly don't know how many people in the field use it. So those are all things to think about with linearity, everybody. Okay? And that'll be part of your homework. Model selection. The book segues into model selection. Sometimes, usually with regression, you may just have one model. You may have, I got these 3 predictors of likelihood. I'm going to choose the hospice, rating the services, rating logistics, my outcome and satisfaction with hospice. That's it. It's just one model. But a lot of times we may have multiple models. Ross may say, well, I think likelihood of choosing should be an outcome, not a predictor. And Ross may say, well, that's an outcome. The likelihood of choosing is a function of the logistics and service. Or Lena may say, well, you know, that's a good model, but I might add how much that thing costs. Right? She may be interested in financial. Or Zach may say, well, you know, if anything, I think we could just pare it down just to rating, service, rating, logistics. So you can have multiple models. Right? Or you may decide that I think rating, service, rating, logistics will come first, and then likelihood will add incremental variance onto a hierarchical approach to regression, which we did a lot in 602.2. So there can be many ways by which you can think about regression, as with every multivariate stats being a model. So, various methods are available for selecting a good set of predictors. The single most important, right, is your knowledge of the area under study, what they call substantive knowledge. Right, your knowledge of the area. Right? Knowledge of domain. And that is crucial, everybody, which means doing your due diligence, doing your homework, doing a lit review. Right? A lit review, you get all that stuff from lit review, meta-analysis, meta-analysis, etc. Sometimes you may use your own opinion, which is okay, but that's not going to go that far empirically. Or maybe your observations. So again, you're going to use substantive knowledge, knowledge of the domain, to help guide your selection of predictors. Guess what? It's not always easy to be comprehensive. If your outcome is satisfaction with hospice, could there be a lot of things that go into that? That go way beyond financial, rating logistics, rating services, and likelihood that you choose? Absolutely. So it's being as mindful and comprehensive as you can. However, not so much that you include everything in the world, which is called overfitting the model. So part of it is substantive knowledge, and that's one way to select the model, or which model you're going to test. As the book indicates, there's good reasons for generally referring to work with a small number of predictors. Good old parsimony, reducing the number of predictors, improves the N to K ratio, which is sample size to regressor, and basically being able to make sense of it. See, the problem is, if you decide there's potentially 10 predictors of satisfaction, do you think we're going to have overlap, everybody?
Yes.
Absolutely. And to make it so bad, you may have predictors that have nice intercorrelation and minimal with that. Now, there are statistical methods that can actually help yield indices for which models select if you have 20 predictors. There's actually these types, and there's one program called Tetrad. These guys are in Carnegie Mellon that you can put in a lot of things and it'll spit out some models that are the best fitting. There are data mining types of algorithms that will spit out the best model. But it'd be great for you to decide that if I'm going to predict diet, exercise, health maintenance, and social influence, those are the big 3. We could probably think of a lot of things that predict diet, right? Depression, all types of variables out there. You want to be as parsimonious and economical as possible, right? Parsimony. What does parsimony mean, everybody? If you went over 602.2? Parsimony, right? Economical in thought and model development. Right? Remember, that's from Lord Occam's Razor. Remember the little picture I showed of Lord Occam? Once again, being economic in your model. Another indication of problems that the book gets into in model selection is looking at the partial and the semi-partial. Remember the partial and semi-partial, everybody? If any of the partials or semi-partials are radically different from zero-order correlations, guarantee you have some linearity. So one way of looking or guiding the model, the book puts it under sequential methods. I'm going to discuss some problems briefly with those. Is you can look at the partials and semi-partials. Looking at the partials. As you remember, can someone remind me what the difference of a partial and semi-part is? Anybody remember? You guys should know, because it's going to be on a test this weekend. They'll be tested. Right now they're in 6022 concurrently, so they'll be tested on it this Friday night. So you better know it by now.
Partial is the part that's completely unique, not shared with the other overlap.
Yes.
The partial is the variance of x1 in y, and x2 is controlled out of x1 in y.
Yeah, so you were kind of explaining the semi-partial. So x2, the partial, everybody, good old partial, which here could be described as ry1 dot 2. Right, the 0 to 2 is going to be partial from the other predictor, and also the variance that's unexplained by the other predictor. And what's the unexplained part of everybody? That. Yeah, yes. Well, actually, yeah, you can call it residual. Some would call that just the unexplained variance, because residual has a meaning of the individual y minus predicted y. So it's actually a summation.
You shade in what would be partial and part, because I still get confused about that.
Okay, I'm not as good as Cohen on doing the Venn diagrams, but I know here, we know that, for instance, here's the overlap, right?
Yeah.
So the unique variance, the partial, y1 dot 2. So here, just the best way for me to present it, Zach, the way to think about it is, if I go ahead and take not only this from this, but the variance that's unexplained by this, right? So it'd be, that's why the partial is always what, bigger or smaller than the semi?
Bigger.
Yeah. When would be the only time they're exactly the same? No other correlation. Whereas Zach, this comes close to what Stacy was saying, is that this would be the semi-partial. Do you see I put parentheses around 1.2? I'm going to take 2 only from 1, right? I'm going to go ahead and just take away that unique variance. And sometimes people call the semi-part the unique. But partial is kind of unique too. So here, what it does, Zach, is it takes x2 from x1, sucks that away, but also the stuff that's unexplained here for the partial. Here, it only does the it only focuses on this. It only focuses on that part.
Okay. I'm still kind of.
Yeah. You know what's
I remember racking my brain like all year. It still does.
Yeah, it's all.
So when you take out that little bottom part you shaded in, that is semi-partial.
Yeah. So if you take away only with x2, there's partials with this and the unexplained.
Okay.
And if you look at the denominator, actually, the denominator, 1 minus r12 squared and 1 minus ry2. We're going to take it away 2. So here the semi would only do this. The partial also adds this part. So basically, you get guess what? You get more variance plus you sucked away. So that being said, everybody, let's look at the partial. Exercise has a 0.536 correlation. The partial is 0.41, the semi-part 0.37. In your opinion, is that a big difference? Just your opinion. No, it's not huge. I mean, it's a little bit. You know what makes the differences seem more evident at? Is if you square them. When you square the correlation, you'll see it's gonna seem more different. But look at this. Look at social influence, everybody. 0.30. The part is 0.028. Is that a big difference? Which means social influence probably has a bigger correlation with the other predictors. Because it's all part of the system, isn't it? It's all part of the system. So this can be a good indication of linearity, and the book puts it under the section on model selection because they talk about potentially using the semi-partials as an indication of the contribution of the variables and as a big part for stepwise, which I'm going to discuss. So please do look at the partials and semi-partials. Please do look at those. Okay, everybody. We already discussed this a lot in 6022, so I'm not going to get too much into it. But in terms of model selection, be careful about rank ordering standardized coefficients. Be really careful about rank ordering standardized coefficients in terms of strength given collinearity. Review my notes from chapter 5 in 6022, where I now have a presentation on dominance analysis. Actually, I show ways to be able, I just did that, as you know, if you're at 6022 now, I show actually how you can break up the R square and mitigate some of those problems with just rank ordering standardized coefficients. Because look here, exercises of 0.42, 0.28, 0.032. So you take exercise number 1, health maintenance number 2, social influence number 3. Because they're all in standardized format. They're all z-scores. But look at the zero, and the zero orders. It does correspond to the biggest, smallest, medium, then smallest correlation. So it does correspond to that. But if you have high collinearity, some of these can even reverse the order. You can find a different order. There's zero order correlations, what's highest to lowest, compared to the standardized coefficient. And that can happen, everybody. So again, be really careful when your boss says, you know what, Chad, you're on a project, but I want you to select the biggest driver of customer satisfaction. Right? You're doing this multiple regression. Which one should we really focus on? And Chad says, well, number 1 is employee courtesy. Number 2 is employee responsiveness. So let's focus on courtesy. Well, what if those have a correlation of 0.7 and they're really similar to the outcome? You'd be focusing on one, right, and sacrificing the other that may be equally of impact. The book discusses one option called sequential methods. As you know, in 6022, stepwise regression is generally a big no-no. Even though many books do it, and you'll see journal articles. Again, is stepwise, as you recall, is that theoretical or atheoretical? Atheoretical, right? You're just putting everything in, you put everything in, and then under model, you hit this thing called stepwise. I have 3 predictors, right, everybody? But guess what the computer does? So the computer uses a partial correlation, and then based on the biggest contribution to the partial, it keeps the variable in. Exercise at the first step, exercise and health maintenance at the second, and look what it spit out, everybody. Do you see a third variable there at the final step of variable entry? Boots it out. So basically what stepwise regression does is this is Stacy's model. And let's say rating logistics is highly collinear with these 2 other variables. And maybe these have a slightly higher correlation. But it still may have a similar correlation. Rating logistics maybe isn't a bad predictor. But in the first step, let's say likelihood has the biggest partial. Puts that in rating service. Then it tries to put in rating logistics, but it's so highly related to rating service, and it has a relatively lower correlation, it boots it out, which means it's computer driven. Now, so I don't use stepwise. Again, I will admit I've been influenced by some negative things said about it by Education Psych Measurement, a premier journal in our field. Bruce Thompson was one of the first editors that said he will not accept any articles that use stepwise. And the main problem is, we said it doesn't cross-validate well, and it's true. Plus, I don't like the computer telling me which variables get to stay in. I don't like the computer saying, we're going to boot this one out. I like to be in control of that.
What do you mean it doesn't cross-validate well?
That sometimes they find that the coefficients you get in a given sample and the variables it keeps in ours when you apply it to maybe another sample, say you've done it at Qualcomm and you want to take the same model, it see if it applies pretty well. Does it come up with the same kind of a predictive power at General Atomics? It doesn't do so well. It doesn't do so well. So that being said, be really mindful and careful about ever using stepwise regression. So stepwise uses the following criteria. It uses a certain F to enter. Or, as the book indicates, it also uses a partial. It may also use the partial correlation to say which ones stay in, which ones do not. And here's Frank Harrell's comments and some of the problems. And you know this from 6022. It yields R-squared values that are badly biased. It gives biased regression coefficients. It has severe problems in the presence of linearity. I like number 9 the best. It allows us not to think about the problem. Number 10, it uses a lot of paper. That's in the old days when we used to print everything out on dot matrix paper. But that being said, you're not thinking about the problem. Now, I do want to say there is a time and a place for these data mining algorithms. You know, for when you have lots of variables, you put it in the system to see what gets spit out. I mean, I do understand why I get someone that has 15 predictors. They're all lab values, cholesterol, triglycerides. You know, have you ever had your blood taken before and seen the lab output? It was like 20, 30, right? Albumin, creatinine. I mean, you've seen it, right? Your potassium. Which ones do you want to predict for certain type of medical outcome? But again, you want to be mindful about it. And usually, even when I work with clinicians, they usually can narrow down to 4 or 5. Right? Like creatinine, I mean, they know their field well enough. They don't put in every single lab value. They've been able to narrow it down. And I just put in some comments here about stepwise. So again, be really cautious about ever using stepwise. And as you see at the first step, we've got 28% accounted for. At the second, 34.9. And it stops at 2 predictors instead of 3. So that's stepwise. That's stepwise. So social influence is gone. Right? The third variable is rooted out. So that's one option they talk about model selection. Again, meaning model selection, what should go in it. Again, if you thought heavily about your model, if Stacy's really convinced that these are the 3 big predictors, and that's good enough, then there's your model. But of course, as you know, there can be alternative models. Another option is called Mallow-C. Basically, it talks about the consequences of underfitting and overfitting. What do you think underfitting means, everybody?
Not finding enough predictors to...
Okay, good. Right, underfitting versus overfitting. Yeah, so this all kind of falls under, right, model specification. Specifying your model. So underfitting, you don't have enough variables in there, which means you've omitted relevant variables. So if you were predicting quality of your leader, what would be a really important variable to leave out? What would be a crucial one that, boy, you really should leave out? Quality of the leader. What would be a crucial outcome?
Communication.
Communication. That's a little on the vague side. You know, whenever I hear communication, I kind of rattle my head. I mean, that's be a little more specific.
Ability to delegate.
Is that pretty important for a leader?
Yes.
Yeah, absolutely. So if you leave that out, where does that omitted variable get sucked into? Yes, it gets sucked into that 1 minus r squared, doesn't it? The unexplained variance. So that's underfitting. What do you think overfitting is? Too many. Do you think there's a lot of things that can predict the quality of the leader? I bet if I had you brainstorm, you could come up, I bet you could come up at the end of the day with 20 predictors. I bet you could come up with what?
Easily.
Probably easily. Yeah, you know what? Probably easily. He could probably come up with 3 that just have to do with his or her financial knowledge of dealing with finance. I bet he'd come up with 3 or 4 just having to do with finances. Right? So absolutely. So, underfitting, overfitting. Here I have 3 predictors. Does everyone see I have 3 predictors? And way over here, get this thing under selection criteria. Okay? key information criteria, and there's the Mallows prediction criteria. So what is Mallows, everybody? Basically, there's a criterion for selecting a model that measures. If you look on page 77 in equation 7, you do not in any way have to memorize that equation. It's basically a way to choose the model. And it's basically P, which is the number of predictors. And you got the variance, sample size, got a lot of things incorporated into that. The residual variance, which is S squared, which is the unexplained variance. So what you would like is, ideally, it's good, and ideally, C, P, now equals P. Now what does that mean, everybody? Meaning, ideally, Callows P equals P, which equals number of predictors. Number of predictors. So, we have 3 predictors, and it gave me a 4. It gave me a 4. So it's a little bit higher. And that's Mallows prediction criteria. I really don't expect you to use it for this class. It's just, it is one thing. Not many people use it very much. But basically gets out if your model is too simple or not simple enough. Too complex. Now, what the book doesn't get into, which we will get into actually with structure equation modeling. Structure equation modeling is the key information criterion and what's called the Schwartz-Bayesian criterion, or sometimes called the Bayesian information. This and this. These are a function. These are a function. We won't get into this, but the log likelihood. The log likelihood of the model plus 2 times m. And where m, sample size of m is number of predictors, or m equals number of parameters to be estimated. This is going to be really valuable when you start getting into more advanced statistics and you want to select models, because what you're going to find is the lower the better. So, in other words, what you're going to find, if I have something like this, everybody, AIC, Model 1, 3 predictors, Model 1, P equals 3 predictors, and let's say I got AIC equals 23.5, Model 2, P equals 4 predictors. So Chad adds an extra one. He adds an extra one. AIC equals 20.3. Guess what? Model 2 wins. Model 2 wins. So soon you're going to see that these, what's called information theoreticals, are really valuable when you get into more sophisticated models. Any of you get into structure equation modeling, multi-level modeling, finite mixture modeling for your dissertation, this is going to be a great index to be able to compare and select models. And you'll see them reported in most journals.
So is the AIC going to always be, you said is it a function of models? So is it always be?
Well, it's not, no.
So are
The mouse
these
is slightly
numbers all
different.
similar? Or not?
No, the calculations are slightly different. But it is used for model selection.
Generally, is AIC going to go down as the Mallows goes up?
No, not necessarily. No, because Mallow is just basically a function of how many predictors. This gets at the number of predictors. This is a function of whatever is used to assess model fit. In other words, with structure equation modeling, you get what's called a chi-square statistic. I take 2 times chi-square plus the number of parameters to be estimated. So the math is a little bit different. Mallows is helpful in saying, did you overfit or underfit? Well, these are great for comparing alternative models. So let's look at let's look at, do you see the IQ key of minus 47, 48? And now let's just add exercise. Now it's minus 22. And we see that R squared went from 35% down to 21. And Mallows now says, boy, we should have 3 predictors. You know, we way underfit. So here what we can see above. So look how this compares, everybody. Look how this compares. Full model, AIC equals minus 47, minus 47.48, and Kalos, P equals 4. And without exercise, 2 predictors. AIC equals minus 22.07. Kalos P equals 3. And R squared for the full model equals 0.215. With 3 predictors, it was 35. So in your opinion, everybody, again, we can do significance testing, but for now, just in your opinion, would you say that's a big difference? Would you say full model, which includes exercise, has an R squared 35%, without exercise, it's 21. In your opinion, does that seem like a big difference? What would be your opinion, everybody, if this was your database?
Yeah.
It seems like it, doesn't it? I agree. And what we see is we have, and just so you know, the more negative, I know this is confusing, but if it's a negative number, the more negative is a lower number. I know that sounds confusing, but think of a number line. And look at Cal, and we can see that R squared is 35 and 21. So is it worth having exercise in the model? Yes or no? I mean, when all is said and done, is it worth having exercise to predict diet and nutrition? Absolutely, I agree with all of them. So these are really pretty helpful indices for guiding model selection.
So if we were just looking at AIC by itself, we want it to be
more negative, or if it's a positive, then less positive. Yeah, because you're going to see some of them, they do minus 2 times the log likelihood. Sometimes they would do the minus 2. So it depends upon how they compute the logarithm of the likelihood. And yet that you have to know the software, the algorithms. But you're absolutely right.
And is there no max or min? It's just
no. It's completely a function of the model. Kind of like variances, right? No, there isn't a magic number. So everybody, these are called information theoretic indices, which have a really long history. A very long history, starting with mathematical statistics. It was called information theory and entropy. It's just this whole different type of statistics for model selection. And just to show you where you can get a lot of this stuff, if I just type in statistics equals all, it'll give all that to you. So everybody, that being said, we've already discussed the partial and the semi-parts. We've discussed this partial and the semi-partial correlations. So for your homework, I do want you to look at one of those two. Look at the semi-partial or partials. I don't care which one you do. Either of them are fine. I usually report the partials. I usually report the partial correlations when I report it to the client. One thing you will notice, if I add up the squared partials or semi-partials, will that add up to the model R squared? What did we learn from 602.2? If I add up all the squared semis or squared partials, will that equal the model R squared? No. Yes.
What's going on when the semi-partial turns negative?
Semi-partial and the end with zero order was positive?
Yeah.
You probably want to know that from this Friday's test, don't you?
That's suppression, isn't it?
Yes. And that's a weird thing to diagnose.
I can't picture that in my head.
I know, it's an odd thing. It's really weird to think that how a correlation can be positive, right? If I have y, x1, x2, Does x2 have any relation to y? Does it to x1? Does x1 have a relationship? So all of a sudden you got maybe a negative relationship, or maybe marginally negative, and it's positive, or the sign's reversed, especially when you get a multiple regression. And suppression means it suppresses the irrelevant variance from y because the shared variance it has with x1 and x2. And it's bizarre. You know it can be really weird, the partials, the square partials, so this can be bigger than the zero order. They change signs. You know when I see stuff like that happening, I'll tell you exactly when I see stuff like that happening. I'm going to pick the simplest example. Y, x1, x2. 0.03, 0.12, 0.67. I'm kind of doing an extreme example. How are we doing with the relationship to the outcome? How are we doing with linearity? Is this worst case or best case scenario for multiple regression? It is the worst. And this applies to when we get to MANOVAs, when we get to factor analysis, when we get to multi-level modeling, structured equation modeling, canonical correlation. This is when you get that reversal of signs. So in other words, this kind of borderline can all of a sudden be negative 0.04, and you're going to scratch your head and say, huh? Right? It's got, especially those borderline values. It'd be weird for a 0.6 to become negative 0.4. That'd be bizarre. I don't think I've seen that. But I've definitely seen the lower correlations contingent on its relationship as part of this closed system do that. And that's suppression. Have fun explaining that to your boss. What's that? Right. So, again, the partial, everybody, the partial correlation, the partial x2 from x1 and the variance in y not explained by x1. Right? So it's R, maybe it's R, y, 1 dot 2. R, let me go ahead and do this here. R, y, 1 dot 2. So you see 2 is partial from y and 1. We're the semi is y, 1 dot 2. We partial out x2 only from x1, the other predictors. Which means the partial will always be greater than the semi-part, except in the limiting case, right? Where there's no intercorrelations. So again, everybody, you now know these are those unstandardized partial regression coefficients. So that means as I go from 1 to 2, 2 to 3 on the self-reported exercise, my DV goes up by 0.368, controlling for health maintenance and social influence. We see that it is significant. We reject the null. Right? Because everybody sees that it's less than 0.05. And here you have the zero order correlation. Exercise got a nice correlation. And there's the partial and semi-part. And there's the tolerance, the collinearity diagnosis. So now you kind of have an idea of the entire output. Someone interpret that 0.42 standardized coefficient for me.
One standard deviation increase in exercise results 0.41, or worst case standard deviation increase in diet nutrition score.
Okay. You could probably massage your wording a little bit, but you're getting there. You're getting there. It means as exercise increases by a standard deviation, there's a 0.42 standard deviation change in diet. You know, about almost half a standard deviation change. So what makes more sense, everybody? And this is where Yarl and Grimm talk quite a bit about this. Which one has the more real-world value, as Yarl and Grimm say? The exercise in the unstandardized or the standardized? Yeah, that's right. But again, a lot of people like the standardized coefficients because then they can rank order. But again, as I said, the really problem, a lot of problems with rank ordering. And please again refer to my notes on Brendan Johnson on rank ordering and dominance technique. And again, what's great is this summer I learned how to do dominance analysis, and I put all that in the 6022 notes. So if you had 6022 before, on the Chapter 5 notes, I actually learned how to do dominance analysis. I learned how to do all subsets regression in SPSS and then plug it into dominance, which is a great way percent as coefficients. Okay, here's another carryover from 6022, everybody. Assumptions, assumptions, assumptions. Again, we've spent a lot of time with this in class. You remember good old homoskedasticity, right, everybody? You probably dreamt and had nightmares about it. So good old homoskedasticity. And the assumptions start on page 90. Again, assumptions matter for virtually every statistic we're doing in this class. Some of them get a little more difficult. Some you really don't check. Exploratory factor analysis. If you like a linear relationship, if you love normality, you really won't be testing that for things like EFA. So here, everybody, as you recall, for the standardized residuals, the standardized predicted value, to be able to obtain the residual plot, you put the Z residual on the y-axis, the Z predicted on the x. So you put both of those on the axes. And there you go. Do you recall if we wanted a nonlinear line or a line? What did we ultimately want to be able to look at the assumption of homoskedasticity? A line. Tell me again what homoskedasticity means. It means constancy of variance across the x-axis. There's the variance, because these are the errors. We would love the errors to be evenly distributed. So if I have, for instance, y minus predicted y, and keep in mind these are standardized values. We would love this. So say I'm using income to predict life satisfaction, 0 to $100,000 a year, to predict life stat. Do the errors across all levels of income look fairly much the same? Right? It's almost as if I could do a distribution at certain levels of income, or each level, and look at the conditional probability of the error given x. Right? It's basically a conditional probability, the probability of the error given x. We would love this constancy of variance, which is pretty much the same of which assumption in one-way ANOVA and the t-test. Which assumption is it the same as the good old one-way ANOVA? Homogenic variance. You got it. You got it. What would we not like, everybody? Yeah, so clustering, or even a nonlinear. Because if you recall, if you have negative residuals, we've over-predicted. Right? Negative residuals, you've over-predicted. Positive residuals, you've under-predicted. Wow, at low and high levels of income, for some reason, we radically over-predict life stat. In the middle, it's kind of under. So here, the residual plot, and then imposing a line, everybody, as you recall, to impose the lowest line is a nice way to examine the assumptions. And as you recall, imposing a lowest line helps get at any nonlinearities. Again, if we forget how to do this, everybody, we go ahead and just do a scatter. Go ahead and go into the set of exercise and health maintenance under plots. Put Z predicted here, Z residual there. Continue, okay. And there's your residual plot. You double click on this. Double click on this. Right click, add fit line, and put lowest right there. Plot. Right, there you go. How's it look, everybody? Pretty good? Thumbs up or thumbs down? Yeah, I agree. I mean, I know you could say, well, look right here. Maybe a little quadratic. But I don't think the quadratic's going to help. There you go. So, what if there's a violation of heteroskedasticity? If there are violations, you may want to play detective with auxiliary variables, right? Or see if subgroups have different levels of variables, right? Right? Add some new variables. Add some new variables. Some variables that were not in postulated model. Or see if subgroups have different levels of error. So that's all, once again, making sense of the residual plots. And the book shows some different examples. As the book indicates, any pattern or clustering of residuals suggests a model violation. Right, so see some groups, and Zach used the word clustering. And just say, what do you mean by clustering? Maybe what you might find is if I do a job satisfaction, predicting job performance, and you find huge residuals here, maybe you'll find these are a lot of people that have been working for the company for 15 or more years. Right? Maybe you'll find there's a type of Zach referred to the word coaching. Maybe you'll find these people that have lower tenure, more errors. Why? Maybe people that have been there longer. Some are really still enjoying their work. Some are what? They're burnt out. Yeah, absolutely. So you may find more variability in the errors, given what Zach referred to as a clustering effect. So a lot of times working with these assumptions takes a little bit of sneak work, a little bit of detective. And that's the residual plot. Also, even though I don't think the book mentions it, you should have normality of what, everybody? You remember me going over this a bazillion times in 6022? Normality of what? The residuals. Right? Right? Exactly. Don't forget. Normality of residuals. Don't forget the normality of the residuals, everybody. So again, how you run this, everybody? Do analyze, regression, linear, and under plot, hit normal probability right there. A normal probability plot will show the residuals. So a lot of people think with regression modeling, that you're going to have normally distributed DV, which is nice to have. It's nice to have that. But what matters more, everybody, is the normality of the residuals. And that's the key assumption right there. All this right here. How do they look, everybody? In your opinion? Not bad. In fact, that looks pretty darn good. So in other words, you could have a DV that's non-normal, but if your residuals look like this, you don't have to transform or do any fancy regression. That'll be fine. That'll be fine. The book segues on page 93 into model validation. Do you see this thing called adjusted R-squared? A lot of people report this. So here we have maybe just two predictors. We have an R-squared of 21.5%. What does it mean? The R-squared you get from your model. When you do your regression model at Qualcomm, or wherever you do it, and you get an R-squared 30%, do you think that's going to necessarily generalize to biotech, to entertainment, to the legal industry? It may or may not. It doesn't necessarily cross-validate well. And what I mean by cross-validate is the full regression equation also. In other words, So if for Qualcomm, your equation is y predicted equals 12.367, which is the intercept, plus 0.467 x1 plus 0.231 x2, and r squared equals 0.198. Can you assume same parameter estimates for another company, industry, whoever you want to cross out A2, will produce the same model fit? You can assume that, everybody. Can you assume that from this equation, that if I plug it in for another company, I'm going to get the same type of model fit? I mean, maybe you will, or maybe you won't. So that's why in SPSS, you get what's called the adjusted R squared. The adjusted R squared, which basically serves almost as, not quite a penalty function, but it takes into account the sample size and the number of predictors. And the book discusses this quite a bit on 93 and 94. Just to show you the formula, everybody, it's called the Wary formula. The Wary formula. And the book, I noticed SPSS uses what's called the Stein. And I don't know that the book discusses both the Wary and the Stein. Okay, on page 96 and 97, it does. Okay, it produces both formulas, everybody. The Wary, and let me show you what SPSS produces. And I plug those in just to show you. Here, let's say we have a sample size of 100, sample size of 100, a model R squared of 36%, and 10 predictors. And 10 predictors. So there we see, everybody, the Wary is 1 minus 100 minus 1, 100 minus 10 minus 1, times 1 minus 0.36, and it's 0.288. Whereas with Stein, it's 0.20. 0.20. So the book actually, I mean, even though it may not say it in SPSS, it actually reports the Stein. What does that adjusted R squared tell me? Well, you know what? If it's radically different from this, guess what? You probably got some problems, and what are those problems? Either what? Small sample size and or, what's the worst case scenario, everybody? Small sample size and or, given this formula, large number of predictors. Okay, well, actually, no, you know what? I just confirmed that. It's Wary that's in SPSS. I'm sorry, not Stein. That's not that model. So, yes, this is a different model. Okay? I'll say not from above. So here's a comparison, everybody, just to show you. I did my own little simulation to take this into here. But let's say I had 10 predictors, 5 predictors, and 3 predictors. Sample size 100, 300, 500. So let's just compare 10 predictors. Look at the Wary and Stein, everybody. And again, SPSS uses the Wary. Look what happens, everybody, with the Wary when we have a model R squared of 36%. The model R squared is 36%. What do you notice as sample size gets larger? Do we get closer or farther away from the model R squared? Closer. Do you see 0.29, 0.338, 0.347? Is that getting closer to this?
Yes.
So one thing, everything remaining constant, meaning the number of predictors, as the sample size gets larger, the adjusted R squared doesn't differ. Now let's vary the number of predictors. If you have 5 predictors and 3 predictors, the sample size of 100, what do you notice happens, everybody, as the number of predictors increase? Do we get closer or farther away to the model R squared?
Farther.
Farther. So what's the 2 take-home lessons, everybody? So the 2 take-home lessons. Here you see what's called shrinkage. This is the impact of what's called shrinkage, which is dictated by sample size and number of predictors. So what's the worst case scenario, everybody? Large number of predictors, and you got it. You got it. That's the worst case scenario. That's when you're going to see a huge difference in the model R squared and adjusted. So it's not a bad idea, everybody, to look at the adjusted. And sometimes it can even be negative. And that may seem mathematically implausible to have a negative adjusted R squared. Guess when you can have a negative adjusted? Maybe suppression. Right, that's his biggest
Word of the day.
He comes home, has an argument with his wife tonight. What's the matter? Suppression.
Also possible.
Also either, yes. Yeah. So that being said, I can guarantee you, if you have an R square in your model R square is something like 3%, and you have 5 predictors, and your sample size is 30, you are right to have a negative adjusted R square. So that you just mathematically can prove it to yourself by the formula. Okay. So that's the adjusted R square, everybody, which again is very, very, very helpful again to look at your model. The book discusses the importance of ordering. We spent a lot of time in 6022 on hierarchical regression, both in the context of polynomial, nonlinear models, and then interactions. So, order does matter, right? For the hierarchical or I know some medicine a lot of times, they don't call it hierarchical because they don't want to confuse it with hierarchical linear modeling. So I notice they use the term sequential approach quite a bit. So here, let's go ahead and have a model where exercise is put at the first step, diet at the second step, and we have an item 19. And let's see what item 19 is, just so you know exactly what it is. It's an overall item. And then we go and put this here. Let's just have this Likert item, just as so there's the DV. I think I'm a healthy person. Just a Likert item. You're actually going to learn a little bit about ordinal regression later. And let's say you say, you know what? Chad comes up with a model that says, yeah, I think exercise is an important predictor of how healthy I feel. But then Layla says, yeah, but you know what? I think diet will add variance over and beyond. And that's a real different way of thinking about a model. So at the first step, 13.9%. At the second, diet adds 4.4%, and they're significant. So that would be a good case scenario for a study. Again, do you see how this is different than stepwise? Stepwise is going to put them both in and maybe not even include both of them at the final step. So, do we have significance for each predictor at each step? You got it. And again, per APA, as you know, APA would put an exercise at the first step and then diet at the second and not include the coefficients. My bias is to include all the coefficients at all the steps to see if things change. And I just noticed in the APA journal that I'm on the editorial board of this morning, I was reading an article real quick, it lists every coefficient from each step. So I felt that was a little bit vindicated compared to APA publication matter. So it does matter, everybody. Look if I did stepwise. The model summary is kind of different. Right? The summary is a little bit different because with stepwise, it may boot out one of the variables. And it does, it boots out one of the variables. However, I do want to say, I can see times when maybe you want to use stepwise. Okay, I'm not going to be so guessing. You may have 12 predictors and you have no idea how to train your model. Stacy is absolutely convinced all 12 predictors are equally crucial. Right? I could see you doing that maybe on an exploratory basis. Okay? Other issues. Order does matter. Order does matter. Layla, that's your name, right, Layla? Layla's theory is I'm going to do an exercise, but then I think diet will add variance over and beyond. Chad thinks diet's important, but exercise will add variance. Same final model, but just kind of a different switcheroo of theoretical importance in ordering. So here you'd say 13% at the first step, 4.4 at the second added, while here you'd have 14, 4.1. For this example, it's not radically different, but it can be. I saw one person when they were defending a dissertation, they were asked, does order matter? And they were a little confused on how to answer it. I said, no, not really. And it does. Because you may find something is significant early on and isn't later on, and vice versa. So again, part of this is all specifying your model. Pre-selection of predictors. Try to specify your model, and this goes with a lot of the techniques we use in this class. Should there be interactions? Should you have nonlinear terms? That's all part of model specification. Okay.
So I was curious about this, but if the model is significant at the last step, is there ever going to be a time where the orders would make it not significant at the last step? Isn't it?
No, it'll be the final, no, because it'll always be the same.
It's more about the R-squared.
The earlier ones, yeah. Yeah, so the R-squared change may not be, but yeah, but the model, it'll be exactly the same, because at the final step, it includes both the predictors. At the final step, Zach, it'll
So why is it so important then, other than the R-squared change?
Because this may or may not, if you had diet here instead of exercise, it may or may not be significant here, it may be significant here. And you wouldn't know that because you've got to have it correspond to your theory. So in other words, you say, now if it doesn't matter, the main thing is why, some people might say, why even do all this? Just put them all at one time. But the fact is you may want to see if diet or exercise adds variance over and beyond. And you'll only get that when you get that R-squared change to be able to look at that. But yeah, at the final step, Chad, it'll be the same. It'll be the final step. It'll be the same regardless of your model. But it's the prior, those antecedent steps, that might change since you know what you have. And I've seen that happen in my own models. I've seen that happen. Okay, everybody. Briefly, we'll take a break about 10 minutes. The book does discuss briefly positive bias of R squared. And it's even known from Keppel and Wickens. They were more impressed with using omega squared. Omega squared, and the book doesn't mention epsilon. Some that don't have such a positive bias. The main bias comes is I go ahead and for my sample, I get a great R squared of 30%. And it may or may not cross-validate with other types of industries. And in IO psychology, we talk about this thing called validity generalization. Does my predictive model generalize across different types of different fields, different types of departments, and it doesn't always. Sometimes it can be positively biased for the sample at hand. Like Schultz found that the R's in homogeneous subsamples were on average 0.34 greater than the total samples, right? Because if you get a lucky draw, you may find that to be the case. So think about, again, there's a chance you'll have a positive bias of R squared. And the book discusses that very briefly. And Ross's favorite subject, which is what, everybody? And I gave you some references, 6022, some classic articles. So, they cited the 2 rules of thumb for selection. Choose variables that coordinate highly with the criteria but have low intercorrelations. Right? Remember that example I showed you, everybody? best case scenario. Y, x1, x2, 0.45, 0.43, 0.08. Wow, that's a nice one, isn't it? Wouldn't you love that for your dissertation? Nice correlations to the outcome, no linearity. Now let's have Ross's nightmare. And ripe for suppression would be what, everybody? Would be ripe for suppression. Let's even add a negative one there. Right? See the problem there? How would you like that interpretation was? Yes, you have. Right. And that's when you get the suppression. And that's when you get weird stuff. And then you get to explain some anomalous findings, such as a positive zero-order correlation now becomes what? It's correlation or regression coefficient, right? Or regression coefficient becomes what? Negative. Or weirder yet, the partial is larger than the zero order correlation. And you guys, it'll happen, believe me. It's going to happen. And that's when you get suppression. So, in an ideal world, try to maximize R, Y, X relationships and minimize what, everybody? R, X, X relationships. Does everybody see that, what I mean by that? Does everybody see what I mean by that? Outliers and influence. Again, this is a review from 6022, so I'm not going to go into extensive detail on that. But here, there's a lot of diagnostics to look at in regression. I think you got the flavor already now. There's more than just pushing a button and getting a regression solution. I mean, the residual parts, though. Looking at normality, looking at the model fit, thinking about variables you've left out, looking at the adjusted R-squared, looking at collinearity. There's a lot for multiple regression. And you can also look at outliers and influence. So as you know, there's just an abundance of riches you can get via the save function regression, such as the Multivariate and leverage values, which gets at outliers on the set of predictors, Cook's distance, which gets at the notion of influence, and the standardized residuals, or the studentized or deleted. All of these indices you can get at what are sometimes called case statistics. You give it to each person, and then you get a really nice outcome. That kind of gives you an idea of the minimum and maximum of some of these, where you can start diagnosing your model, for any potential problems. So why don't we come back from the break, and we'll look at these diagnostics. And then hopefully we will be able to start lecturing about MANOVA. Okay, everybody? Go take 15, 10:25, come back.